In this video, we're going to discuss the decision rule of the receiver. Now let's review the output of the receiver. If digital 1 is transmitted, we know the output of the correlator is increasing positively, and at TB, at the end of the pulse, it reached the maximum. If digital 0 is transmitted, it's decreasing with time. At the end of the pulse duration, it reached the minimum. So we can see that really the 0 point here, 0 values, is really the separation point for digital 1 and digital 0. So the decision rule of the receiver is this. So at the end of each pulse duration, I call it value of y. I'm going to get into this in more detail shortly. I look at the values. If the value is greater or equals to 0, I call it digital 1 is transmitted. If it is less than 0, I call it digital 0 is transmitted. And you can put y equals to 0 exactly goes to 0. It doesn't matter, only 1 point. So this is a decision rule at the receiver. And by the way, this is called hard decision because the receiver is compared with a hard value, 0 in this case. So this is a hard decision. The counterpart is soft decision, where the output is the probability. The probability of 1 or the probability of 0. So that's the soft decision. Next, we'll discuss the probability of such receiver making error. The error means that the decision was wrong based on the signal of transmitted. So if digital 1 is transmitted, if the receiver decided, okay, the received signal is 0, in such case, the receiver made wrong decision. The error occurs. Before we do that, let's review the random variables. Let's review the Gaussian PDF function first. Gaussian PDF function with mean, m, and sigma squares. The PDF function is this format here. Let's look at an example. If this random variable x in normal Gaussian with 0 mean, the variance equals to 4, the PDF equals to 1 over square root 2 pi sigma squared. This sigma squared inside the square root. This is the same thing here, the scalar. And the exponential part, and x minus the mean squared. Denominator is 2 sigma squared and 2 multiplied by 8. And this equals to 1 over 2 pi, that is 2, and e to the power minus x squared divided by 8. Okay. Now, let's say if I have a random variable y equals to x plus 2. What's the distribution of y? What's the PDF of for y? First of all, x is Gaussian, and this is shifted by 2. Therefore, y is Gaussian as well. Next, we need to find the mean Gaussian, this Gaussian random variable, and variance of y. A random variable shifted by a scalar. We have all of this property of the mean and the variance. If a random variable is shifted, the mean is shifted. If a random variable is shifted, the variance does not change. Therefore, expectation of y equals to expectation of x plus 2, and expectation of x, that's 0, that equals to 2. What is the variance of y? That equals to variance of x, because variance measures how spread out the random variable away from the mean. The mean is shifted, although this random variable is shifted. Therefore, the variance does not change. It's the same as the variance of x. that equals to 4. Therefore, the PDF function of y, fy, and y that equals to square root sigma equals to 2 because sigma squared equals to 4, and e to the power minus y, in this case, expectation of y that equals to 2 now, squared, and sigma squared, that's the same, 2 multiplied by 8. So this is a PDF function of y. After this review, let's look at the output of the receiver. To simplify the notation, I drop this bracket TB. I use notation of y, just y, one scalar. This is a value to represent the output of the correlator. This is the same notation in our textbook. Before we have the integrator at TB equals to SM plus N. Now I have Y equals to SM plus N. SM, that's the coefficient for geometric representation for the transmitted signal. This N, this is a noise, which is Gaussian. 0 means the variance is a naught divided by 2. What is the PDF function of Y? This is not random. There's no randomness in the transmitted pulse. It is determined. If we know SM depends on digital 1 is transmitted or digital 0 is transmitted, this PDF function that equals to this. Y in this case is Gaussian with the mean of SM. The variance is a naught divided by 2 now. So therefore the PDF function is this. So now let's say if digital 1 is transmitted, Y is Gaussian, SM in this case equals to square root EB. The variance is a naught divided by 2. If 0 is transmitted, in this case, the geometric coefficient is minus square root EB, but the variance is still a naught divided by 2. Now, if I want to plot this PDF function, digital 0 is transmitted, the mean is minus square root EB, that's here, minus square root EB is Gaussian. Now, under what conditions that the receiver will make error? We know the decision rule is to compare with 0. If the value of y greater than 0, then the receiver will decide digital 1 is transmitted. So in this case, what's the probability error? The probability error is this shaded area when y greater than 0. Because in this case, digital 0 is transmitted. This is the output distribution because of the noise. Now this noise can make the receiver to make wrong decisions. This noise is powerful enough such that the received signal is greater than 0 now. Then under this situation, the receiver will claim digital 1 is transmitted, but really digital 0 is transmitted. In this case, the error is made. The same thing when digital 1 is transmitted. What's the PDF function? So this is a square root EB. The PDF function is here. Okay, the mean is square root EB. Suppose this is a 0. This is 0. If the noise is powerful enough, the received signal is negative now. Under this situation, the receiver will claim, okay, digital 0 is transmitted, but really it's not. Really, the digital 1 is transmitted. If digital 0 is transmitted, the probability of error is y greater than 0. If digital 1 is transmitted, this error, the error is probability of y less than 0. And this is the tail probability. And what is this probability? And this probability is Q0 minus, the mean is minus square root EB. And what's the sigma? Sigma is square root n naught divided by 2. And this is a Q square root EB and square root n naught divided by 2. What is this probability of 1 is transmitted? That equals to 1 minus probability of y greater than 0. And probability y greater than 0, that equals to probability. I can use the Q function here. Equals Q0 minus, in this case, the mean is square root EB. And the variance is n naught divided by 2. Right. This is 1 minus Q minus square root EB square root n naught divided by 2. And we know, for example, this equals to 1 minus, right? So we take this out, that equals to, this is the same probability, this is the same tail probability when 0 is transmitted. So now I summarize the error of probability. So now let's summarize. Suppose X is transmitted. X can be digital 1 or can be digital 0. X hat, that's the decision. And X and X hat are digital bit 0 or 1. Now the probability error is equals to probability of X hat not equals to X, which has two cases. When digital X is transmitted and the decision is 1, and when digital 1 is transmitted, but decision is 0. So using the total probability, we sum them up. These two cases are up. This is the probability of making an error. And we know this probability, that's this tail probability. And this equals to Q of square root EB divided by n naught. This is exactly what we derived here. And if we do a little reorganization here, take out, organize the square root there, that's 2EB divided by n naught. Exactly what I written here. This is square root 2EB divided by n naught inside the Q function. When digital 1 is transmitted at the same thing. So therefore, what's the probability of error? That's the Q function of square root of 2EB divided by n naught. And we have another terminology is EB divided by n naught is called bit energy to noise ratio. And this is a signal to noise ratio and people normally use as well. The signal to noise ratio really depends on the situation. This is EB over n naught. And this is EB, should be curly. This is curly. This is the same thing. We want to plot it. What does it look like? And this is a probability, and this is a log scale. In the signal to noise ratio normally expressed by dB. In dB values, we take 10 log 10, the values, and this is curly EB. And so I 10 dB. 10 dB means that the EB, the signal EB equals to 10 times of n naught. Because if this ratio equals to 10 log 10 and 10, that equals to 1, you multiply by 10, that's 10 dB. So therefore, which means the signal is 10 times than the noise power. Now, at this level, the probability error is 10 to the power minus 5, which means that if I transmit 10 to power 5 data, there's one chance I will make error. So this is a probability of making error. And this is very good. In practical systems at 10 dB, we do not have this performance because of the channel. The channel is random. It will make this performance worse than this. Now let's do a recap. The probability of error is when the decision does not equal to the transmitted signal. There are two cases. When 0 is transmitted, the decision is 1. When 1 is transmitted, the decision is 0. There are two scenarios. And we're assuming that probability of 0 transmitted and probability of 1 transmitted in the data stream, they are the same, half and half. So which means that if I have a data stream coming 0 and 1 and 1, 1, 0, 0, everything, the probability of 0 occurs equals to probability of 1 occurs. They both equals to half. Both equals to half. Now this probability, we know this is a tail probability. When 0 is transmitted, the PDF function is this. The mean is minus square root EB. The error occurs when the value of y greater than 0. We know the probability of y greater than 0, this tail probability equals the Q function of square root double of EB divided by N naught. And we have the same value when 1 is transmitted, but the decision is 0. And we sum them up. There's a half here, there's a half here. The probability error is really just one term.